Alfred Wegener and the Origin of an Idea. In the early 20th century, a young German scientist named Alfred Wegener noticed that the African and South American coastlines on opposite sides of the Atlantic Ocean seemed to fit together as if they were adjacent pieces of a jigsaw puzzle. He then launched an idea whose pursuit became one of the most fascinating chronicles in the history of science. Born in 1880, Wegener began his career studying meteorology. While a university student, he took part in an exploratory expedition to Greenland in 1906. He developed a fascination for that ice-covered island in the North Atlantic that continued throughout his life and was eventually responsible for his premature death. Although his formal profession was meteorology, Wegener was intrigued by the matching of continents across the Atlantic Ocean. He realized that the jigsaw-like fit suggested that the continents had once been joined together and had later split and drifted apart. But as a good scientist, he recognized that this similarity alone did not prove that a single large continent had split apart to form the modern continents. Therefore, he began seeking additional evidence in 1910 and continued to work on the project until his death in 1930. The idea that Wegener developed and pursued for 20 years is known as the theory of continental drift. Wegener's evidence for continental drift. Wegener accumulated evidence of many different kinds indicating that all of the Earth's continents had once been joined together, forming a single large landmass. Fit of continental coastlines. Studying world maps, Wegener noticed that not only did the continents on both sides of the Atlantic fit together well, but that other continents, when moved properly, also fit like additional pieces of the same jigsaw puzzle. He constructed a map of the Earth based on the fit of continents. On his map, all of the continents were joined together, forming one supercontinent, which he called Pangaea, from the Greek root word for all lands. The northern part of Pangaea was commonly called Laurasia, and the southern part Gondwanaland. Evidence from fossils. Mesosaurus is a sharp-toothed reptile that looks like an alligator. Mesosaurus fossils have been found in South America and Africa, but nowhere else in the world. It is difficult to imagine how a slow, wallowing, freshwater swamp dweller could swim thousands of kilometers across the Atlantic Ocean to populate two different continents. However, Wegener noted that on his reconstructed map of Pangaea, the fossil sites were immediately adjacent to one another. Wegener also mapped the location of the fossil remains of a fern called Glossopteris. Fossils of this plant were found in Antarctica, Africa, Australia, South America, and India. Why would the same species be found on continents separated by thousands of kilometers of ocean? To solve this dilemma, Wegener plotted localities where those fossils were found on his Pangaea map. Again, all of the fossil localities are in the same region of Pangaea. The fossil evidence led Wegener to an additional interpretation of Pangaea's history. He observed that rocks of Ordovician through Triassic age, 505 through 208 million years ago, from Africa and South America contained identical fossils. Rocks younger than Triassic age, however, showed development of different species on the two continents. Wegener reasoned that the Atlantic Ocean basin began to open and tear Pangaea apart at the end of the Triassic period. Rocks that had formed before this separation contained identical fossils because the plants and animals had evolved and spread throughout Pangaea. Rocks formed after Pangaea split up contained different fossils because evolution had followed different paths on the separated continents. Wegener was unable to determine the absolute time when the Atlantic Ocean began to open because radiometric dating had not yet been developed. However, we now know that the end of the Triassic period, when Pangaea started to split up, was slightly more than 200 million years ago. Evidence from paleoclimatology. Paleoclimatology is the study of ancient climates. As both a meteorologist and a geologist, Wegener knew that certain types of sedimentary rocks form in certain climatic zones of the Earth. Glaciers and glacial sediment, for example, concentrate in high latitudes. Deserts and the rocks that form in deserts cluster around latitudes 30 degrees north and south. Coral reefs and coal swamps thrive in near equatorial tropical climates. Thus, sedimentary rocks reflect the latitudes at which they formed. Geologic evidence. Wegener noticed several instances in which an uncommon rock type or a distinctive sequence of rocks on one side of the Atlantic Ocean was identical to rocks on the other side. When he plotted the rocks on a Pangaea map, those on the east side of the Atlantic were continuous with their counterparts on the west side. For example, the Cape Fold Belt in South Africa consists of a sequence of rocks similar to rocks found in the Buenos Aires province of Argentina. Plotted on a Pangaea map, the two sequences of rocks appear as a single continuous belt of folded rocks. Figure 1 also shows this relationship along with two other localities of geological continuity between South America and Africa. Wegener's mechanism for continental drift. Wegener's theory of continental drift was so revolutionary that skeptical scientists demanded an explanation of how the continents move. They wanted an explanation of the mechanism of continental drift. Wegener had concentrated on developing evidence that the continents had drifted, not on how they moved. Finally, perhaps out of exasperation and largely as an afterthought to what he considered the important part of his theory, Wegener suggested two alternative possibilities. First, that continents plow their way through oceanic crust, shoving it aside as a ship plows through water, and second, that continental crust slides over oceanic crust. These suggestions turned out to be an ill-considered and fatal step for his theory. Physicists immediately proved that both of Wegener's mechanisms were impossible. Oceanic crust is too strong for continents to plow through. The attempt would be like trying to push a matchstick boat through heavy tar. The boat, analogous to the continents, would break apart. Furthermore, frictional resistance is too great for continents to slide over oceanic crust. The calculations of the physicists were quickly adopted by most scientists as proof that Wegener's theory of continental drift was wrong. Notice, however, that those calculations only proved that the mechanism proposed by Wegener was incorrect. They did not disprove or even consider the huge mass of evidence that he had collected to indicate that the continents were once joined together. This obvious distinction appears to have been missed by many. During the 30-year period from about 1930 to 1960, some geologists continued to debate the continental drift theory, but it was largely ignored by most of the scientific community. Wegener's fascination for Greenland led him to undertake a third expedition to the ice cap in 1930. One of the shortest routes of the newly available air travel from northern Europe to North America involved flying over Greenland. To make the flights safer, it was necessary to have weather information from Greenland. Part of Wegener's mission was to establish a weather station near the center of the ice cap. In the late summer and autumn of 1930, Wegener and his companions freighted supplies and equipment by dog sled to establish the station, which was to be manned by a single meteorologist through the Arctic winter. Upon looking at the meager seeming pile of supplies and considering the long winter ahead, the man who was to stay announced that the supplies were insufficient and he would not stay unless he had more food and gear. The days were becoming short and winter was coming rapidly. To save the expedition, Wegener and his assistant, an Eskimo named Rasmus Wilhelmsen, set off on Wegener's 50th birthday to obtain additional supplies. Wilhelmsen was never seen again. Wegener's body was found, frozen, the following summer by a research party. An assessment of Wegener's theory. Much of the theory of continental drift is similar to plate tectonics theory. Modern evidence indicates that the continents were joined together just as Wegener's Pangaea map showed. Furthermore, Wegener's interpretation of when Pangaea started to split up at the end of Triassic time about 200 million years ago is also validated by recent data. He accumulated a vast amount of accurate data that firmly supported his theory that the continents were once joined together to form Pangaea and later had drifted apart. The results of his work are a contribution to science of which any geologist would be proud. Why, then, was the theory of continental drift nearly universally rejected? Most scientists of the day were apparently stuck in their intuitive notion that rocks are too hard and solid to permit the movement of continents. When physicists proved Wegener's mechanism impossible, the scientific community was only too willing to reject his data as well. Therefore, his careful work and well-thought-out conclusions were ignored. The plate tectonics theory resurrected Wegener's theory of continental drift and offers a reasonable mechanism for the movement of continents. The resurrection occurred unexpectedly in the 1960s as a result of new information about the Earth's magnetic field and the way in which rocks preserve a record of the Earth's magnetic history. Today, most geologists recognize the excellence of Wegener's contributions.